I do mostly work on basically nano materials and nano devices based on semiconductors. Of course, some of them have got probably some future applications in some computing, probably quantum computing also. So I have divided my lectures in two different ways. The first half of the lecture will be mostly introductory for particularly I was talking of quantum devices, particularly for the students mostly, so that they are introduced to the subject. And second part is basically group 4 semiconductor nanostructures, on which we do some experiments at IIT Kharagpur. We grow materials, make some nano devices, and we'll be talking about that. Okay, so start with silicon based quantum structures, because you need, if you want to make a quantum device or quantum structures, one of the pathways is using a semiconductor nanostructures. Now it is easily achievable using 3-5 semiconductors, 2-6 semiconductors, but unfortunately none of them are compatible to make a device fabrications. If you want to make a devices with a silicon CMOS technology, so you have to make these devices either with silicon or germanium, so any element from the group 4 or even maybe carbon or the alpha tin. So that's the motivation. And the other motivation is that before this quantum computing, there is some more term called optical computing or photonic computing. Can you do this information processing inside the chip using photons? So even that speed will be much, much higher compared to our conventional computer that you use. So unfortunately that has not yet been achieved, though it has been talked for last 30 years or so, because one of the problem is that you don't have a silicon laser in the production or in the market, or it's not possible to make, because silicon is basically indirect bandgap material. And as you know that the recombination of the electrons and holes, if they are in the same momentum at a momentum point, then only they can give radiative recombinations and they can give light emissions. So that is still a challenge, and there is a possibility that could be solved even before making a quantum computer as such. And of course, some of these quantum devices can be some of the elements for the future quantum computing. So some of the possible applications which we are thinking and other people are also working. Currently, some of them already has been implemented. Some of them are probably the futuristic applications. So one possibility is that, as I said, is it possible to get light emission from silicon-based materials in the visible range? That means, can we get silicon LED or the laser? So that is still a challenge. If not, can we at least get a laser in the fiber optic communication range, so that I can use that silicon for as a along with the fiber optic for at least for enhanced communications. So that is somehow a little bit possible nowadays with new technologies. I'll present a little bit on that. The other quantum devices which are very popular and which have been almost actually not available commercially, but the people have developed in different labs, is basically quantum well and quantum dot infrared photodetectors. Actually, they are very useful for a night vision imaging. As you know, if you go to any, if you are in a spy satellite or in the war field, you have to actually capture the image in the night. So basically, they can these photodetectors can observe or detect the black body radiations. So that is very useful. In fact, if this is extended, we get another kind of devices which works in the terahertz frequency range. So terahertz is some frequency range between the optical frequency and the electrical frequency. So this terahertz frequency range also could be generated by using inter-subband transitions. There are other terahertz lasers also, but those are very costly. So if you want to make a solid-state terahertz laser generation and detectors, the possibility is probably using a inter-subband transitions in a silicon quantum well or quantum dot. Of course, electronically, this quantum dot can act as a memory, or which is called a nanoelectric memory or single electron memory. That is possible. And other things which people have done with a lot of advancement in electron beam lithography and other things, single electron devices, resonant tunneling diodes, and spin-based devices. I have underlined them because these are some of the candidates actually. We can say semiconductor-based candidates for probably future quantum computing components or systems probably. So these are still possible. Okay, so as far as the physics-wise, the basic physics is that we call the system has gone to the quantum limit when you get some kind of either energy quantization, charge quantization. In fact, we'll talk about this a lot in your experimental results when I put it. When the size of the semiconductor actually is reduced to the size of the excitonic board radius of a material. So as you know that in semiconductor you have got both electron and holes. So they have a strong Coulombic interactions between them, and if these Coulombic interactions are stable, actually they can give rise to what is a new particle called excitons, and this exciton has got a particular lifetime, and they can be used for actually optical transitions or optical processing. So if the size of this is like almost like a Bohr radius of hydrogen atom, and we know that this radius is about 0.53 angstrom. Okay, but when you go to a dielectric medium with a different effective mass, the size becomes about 5 to 10 nanometer. So if the size of the dimensions of the material can be reduced to that, actually you get a energy quantization, which is basically we call that blue shift, which will show something. Then similarly, you can have a charge quantization. This particularly happens for a single electrode transistors or a Coulomb blockade devices, that if you try to find out the capacitance of the small area where the charge is stored, if this capacity or the charging energy is more than thermal energy of the electrons, you can see that conductance is quantized, or you can get the charge quantization. And this ballistic transport happens for actually resonant tunneling diodes or any kind of tunneling devices. When the thickness of the barrier is very, very small, actually what you can, below the mean free path of the carriers, actually the carriers can switch on, or the devices switched on at a very high speed, which we call as the ballistic transport. So these are the three things that we normally see in a, so-called the quantum devices. And of course, when you talk about quantum computing, I think many experts are there, they are talking about the coherence, phase coherence, time coherence. Of course, you have to make a quantum coherent devices. That is actually basically the challenge. So as I said, some of the, so you talk about in that case quantum interference, quantum tunneling, quantum entanglement. So these are, I am sure that this is being talked a lot in this conference or the school. So some of the solid state devices can be, as I said, some of these either resonant tunneling diodes. I'll talk that, see how this works. Some of the quantum dot based devices, or some of the spin based devices that we get typically on spintronic materials. Of course, the challenge is to, as I said, that you have to have a very high coherence length or maybe high coherence time. Unfortunately, most of the semiconductor, this coherence length and time is very, very small. So that is a big issue to see. Like for tunneling devices, there is a big problem. There is always a fluctuation of the thickness, and the tunneling probability is exponential depending on the tunneling thickness. So it's very difficult to get these devices, all quantum dots of the same size or all tunneling barriers of the same width. So that creates a lot of problem to make this kind of structures of the devices. Okay, so that is the basic introduction. So this is mostly for the students. I mean, the question can be always asked that when you call this device is a quantum, or the device is nano, or the material is nano, so-called. As far as the physics point of view or the electrical point of view, we have to see that whether the electrons or the carriers in the material actually can be now actually described classically or quantum mechanically. That means whether the electrons has got a now behave as a wave or behave as a particle. As you know that electron will behave as a particle if the dimension of the system is comparable to the so-called the de Broglie wavelength. In fact, other terminology I have used, it can be as the exciton Bohr radius. So let us talk about the de Broglie wavelength, because it's very easy to calculate, as you know that. As you see that, yeah, you can, this de Broglie wavelength, actually the de Broglie wavelength depends upon basically that, ultimately depends upon the effective mass of the material and the temperature of the material. So if you use the so-called the Heisenberg uncertainty principle and use the E equal to P square by 2m and use the momentum you write like this, you can easily find out the basically what is the de Broglie wavelength. And let us try to find out this value for a typical practical semiconductor system. If you see, okay, if you take effective mass of electron in a semiconductor system is about 0.1 of the free electron mass, and temperature is room temperature 300 K, the delta X we can get as about 5 nanometer. We can say that if you get a material or a quantum dot or a size less than 5 nanometer, we are supposed to see so-called the quantization of energy. And so that is easy to achievable nowadays because the experimentalists make these devices with two different methods. Either use a very sophisticated lithography system, or they can grow the material by what is a technique called a self-assembly. Now I have just given this emitter for two very important semiconductor. One is gallium arsenide and one is silicon. And gallium arsenide has a lower effective mass. That's why the de Broglie wavelength of the gallium arsenide is much more than silicon. So that's why it is easier to fabricate so-called these quantum devices in gallium arsenide much more easily compared to silicon. So, and of course it depends on temperature. If you reduce the temperature, this length will go up. So that's why most of the devices work better at lower temperature. But for a practical devices, definitely it should work at a room temperature. Okay, so yeah, schematically you show like this. If you reduce the dimension from a 3-dimensional system, actually this is basically can be done by growing a thin film, very ultra thin film in the order of 5 to 10 nanometer on a substrate. Suppose this is the thickness of the film. As you know, in the XY directions, now this electron behave as a free particle, but in the Z direction, the motion of the electrons are quantized. So this we call actually so-called the 2-dimensional system, and which is known as the quantum well. And if you start reducing or cutting the dimension just by using a knife or lithography system, make a kind of a only 1-dimensional system where the electrons are only free to move, as classically as a free particle only in the probably along the length, we call it a quantum wire or the 1-dimensional. And of course, the best properties should be actually achievable that if you can confine the motion in all 3 directions. So we call basically is a 0-dimensional system or a quantum dot. So I told about the energy quantization, which is known to all of us because we have done in solid state physics and the quantum mechanics. The one more most important thing is that not only this quantization of energy level, one more important thing happens that how this density of states of these systems 0D, 1D, 2D changes compared to the bulk material. In fact, for the bulk material or 3-dimensional material, the density of state is continuous in nature. So if you start filling the electron can have all possible energies from 0 energy to energy E with all possible distributions. So this is the density of state is parabolic in nature. This is the density of state in the y-axis and this is the energy in the x-axis. So of course it's parabolic in nature. As soon as you reduce the dimension and make it a 2-dimensional quantum well, this is basically behaves like a staircase characteristics. And in fact, the exact the dependence has been plotted here. In case of bulk material is proportional to the e to the power half, and in case of quantum well is independent of the energy. Only it goes to the next quantum number. Actually, it goes to the next energy level. But for this, for a same quantum number is independent of energy because this remains same. Okay. And for the 1-dimensional system, as you see that it's become much more narrower and narrower. And if you take a perfect theoretical quantum dots or a 0-dimensional system, this density of states is a delta function, very short in nature. So it's analogous to so-called the atomic states. So whatever the lasers we can get in the atomic state lasers, ideally if you can really make a quantum dots with a with the same monodispersed size and distribution, ideally the density of state is very sharp. But as you know, that practically it's very impossible to make the so-called the dots or the materials in the same size. So this is always the broadening here. So that's why this is one of the most preferred system to make this kind of quantum devices. Okay, so the first example I will see that this effect of the density of states in a particular semiconductor lasers. So this is a little bit old slides. This shows trend up to 2010, and that how the semiconductor lasers. We know that how the how the semiconductor microelectronics has gone from micron level to the nano level, and how the density has gone up. We can put a similar roadmap for an optical system. This is basically in a laser, the most important figure of merit or the parameters is the threshold current density. That means how much power I have to put in this laser so that I can get this lasing action to take place for the whole day or for the whole duration of the conference. And you see initially starts with a typical gallium arsenide p-n junctions of about million ampere per centimeter square. Then from homojunction, people came to the heterojunction. In fact, you know that alpha of this Russian physicist got the Nobel Prize for this heterojunction semiconductor laser. That was the concept was given by them. And finally, from heterojunctions to basically this is quantum well. And finally, that you, as you said, that if you make quantum dots, the density of states now becomes very, very sharp. As the density of states becomes very sharp, the energies are confined within a very small energy level. So basically, that threshold energy for this quantum system actually becomes very, very low. So people are going probably nowadays with a threshold current density less than 1 milliampere per centimeter square or 1 ampere per centimeter square. That means you can drive a laser with a probably, current of about micro to milliampere. Okay, so this is still the part of the introduction that we know that in the textbook that if you take three-dimensional system or one-dimensional system, the energy is quantized and gives like this. It depends upon n square, h squared by 8ml square. In case of if you just quantum dots, actually that we used almost a similar model with some modification. The first modification was given by this brass. Then there's a lot of modification for different systems. So you can see the second term more or less remains the same. I mean, consistent with the particle in a box. But since we have got now electrons and actually holes, so there is a basically energy which has to be subtracted, the Coulombic energy. So energy is changed a little bit as a function, and which goes as a function of size as 1 by r. So the total energy is basically the band gap of the semiconductor plus the quantization energy minus that Coulombic energy. And there is one more correction term, but it does not depend on the size. So it follows the typical quantum mechanics particle in a box, but with some modification. But finally, what we get is something like this. In case of semiconductor, we plot the so-called this is the plot for a schematic for a quantum well. We have a conduction band. So what we assume here, you want to make a quantum well in case of a semiconductor, you always first need a heterostructures. That means we need two semiconductors with different band gap. So that one of them low band gap semiconductor works as a well, and the high band gap semiconductors works as a barrier. So that is a must. So in this case, actually, a well is flanked by two barriers with a high band gap semiconductor. And if this width of the well is low enough, below the de Broglie wavelength, we get a quantization of energy. And as you see, this is the ground state energy for the electron, and this is the ground state energy for the hole. In fact, in case of valence band, is more complicated. You have got heavy hole, light hole, spin orbit split holes. So a lot of complicated things are there. But we take the heavy hole as the probably has got the lowest energy, so that's why you take that. That is the ground state energy. So initially we started with semiconductor with a band gap Eg, whose band gap was given like this, and because of the quantization, the band gap has gone up like this. And if you have got a very high barrier, actually, you can have not only the ground state, you can confine some of the other states also. In fact, this is also a challenge. It's not very easy to get a combination of a low band gap semiconductor with a high band gap semiconductor, so that you get a very high barrier height and confine many energy levels. It is theoretically it is, but experiment is very difficult because there's a lot of problem of the growth of the semiconductor with a different lattice mismatch. But anyway, so what we can say, this quantum size effect is that as we reduce the size, as you know that it goes as a 1 over L square, this spacing increases. So basically you can tune the band gap of the material. That is actually one of the biggest, use of the quantum mechanics or to make a quantum well lasers of any wavelength. Because naturally you don't have the semiconductors of all wavelength. Suppose for fiber optic communications, only 1 or 2 wavelengths are actually passes through the fiber optics with a very, very less absorptions. It's about 1.54 micron. But unfortunately, you don't have any semiconductor which gives a emission of 1.54 micron. So you have to alloy different semiconductors with different size of this quantum well so that you can get exactly the same band gap. So this quantum size effect is very important for many other applications for semiconductor doped glass. These are the pictures have been shown by almost everybody who talks about nanoparticles and other things. These are the solutions actually colloidal solutions of the semiconductors, in fact, first developed by Faraday, Michael Faraday. As you see change the size of the particles, even the same particle like cadmium selenide, you see that you can change the emission or the absorption color, which basically depends upon the quantum size effect. So this is one of the applications to make a different kind of glasses or different kind of matrices with different colors, or absorbs and emits lasers of different wavelengths. Okay, so I'll come to this also, that till now we have seen that if you have one barrier, one high band gap semiconductor, low band gap semiconductor, we make heterostructures. So heterostructures can be of different type. It can be type 1. In this example, I have taken a gallium arsenide, is a very common example, low band gap semiconductor, and gallium aluminum arsenide of a particular compositions as high band gap semiconductor. They have been chosen because they have got the same lattice constant, so one can be grown on another without any defects experimentally. And as you see that we have got a conduction band offset and we have got a valence band offsets. So our quantum energy state has to be confined within this, within these offsets in this. So if I put one more barrier this side, actually we got what is called that quantum well, that single quantum well that I was showing. If I repeat the structure, we got actually the multiple quantum wells. Now, these quantum wells can be well separated, so they do not interact with one another, or they may couple with one another actually. In fact, if I just use this one and repeat it more and reduce this spacing between them, actually what we call actually is a superlattice. Since this is a type 1 heterostructure, we call it a type 1 superlattice. So we get something new and unique properties in the dispersion reluctance in case of superlattice, which I'll show in the next slide. And other possible band alignment in heterostructures can be actually type 2. In fact, there are a lot of theories, but still these theories are not really known that which combination of the materials make a type 1 or type 2. It's not a unique theory there. So in this case, as you see that we have used two different materials, the indium arsenide and gallium antimonide actually is one combination. As you see, this band alignment is little bit different here. So you get a very huge conduction band offset and huge valence band offsets, which is much more than the band gap difference between the two materials. So in fact, these type 2 materials, if you just continue to actually make it, you can get some kind of type 2 superlattice. And type 2 superlattice is nothing but actually the example of a very deep quantum well, as you see. This is quantum well, this is quantum well, this is quantum well. It's a very deep quantum well compared to the so-called type 1, alignment or type 1 superlattice. So what you get in this kind of superlattice is something like this. In fact, if you put several quantum wells, 50, 100, 500, actually there is no limit. Only limit is that how much can you grow and what is your growth rate and how is the uniformity of this barrier and the well. That is the only limit. It's very difficult to grow with uniformity over a large number of quantum wells. So what you do, if you put this together, actually the wave functions in each quantum well starts overlapping, and we get again a block oscillations of the super block states in these quantum wells. So which is different from the block oscillations that we get in normal crystals. In crystal we get the periodicity basically which gives us the band structures, which depends upon the lattice constants of the material. In this case, the periodicity of this growth of the material, that means what is the thickness of the well and what is the thickness of the barrier, gives some kind of periodicity, what is known as the superlattice periodicity. But actually what is important is that you get something like this. So earlier you had only conduction band and valence band. Now inside the conduction band, you get formation of subbands or formation of mini-bands. As you see that in the conduction band now you have got a one mini-band here and one mini-band here. So there can be now electronic transport between these mini-bands. So you have basically what you can say that if you can make a system like this, you have tailored a material which has got a inter-subband transitions or some kind of a mini gap between the two labels in the conduction band and again the gap between the band gap between the two labels in the valence band. And if we try to we have calculated some of these values using some combination of aluminum gallium arsenide and gallium arsenide, and this thickness of this both barrier in the well is in the range of 9 nanometer. We get a energy separation between, so this is the E1 is the ground state energy level in this one, and E2 is the fast excited state, and as you see the energy difference is about 60 millielectron volt, which is much more than so-called the room temperature energy is about 26 millielectron volt. So you can get 3 times that energy. That means you can make a superlattice. You can have a superlattice transport in a semiconductor which works at room temperature and which can give you lasers. In fact, these are very useful to get a unipolar laser. I talked about the terahertz also. That terahertz means basically that very, very high frequency. So 1 terahertz is about 4 millielectron volt in terms of energy. So about 60 terahertz means about, 60 millielectron volt means about 15 terahertz. So you can really get lasers or detectors out of this kind of superlattice structures which will operate in the very, very long wavelength radiation range or the terahertz frequency range. Okay, so I think these are part of our all introduction, very general for the particular audience to the students. So quickly we will go back to our own work. One more important thing is that when you take the transport, this quantum resistance, we define something called quantum resistance, which is different from the classical resistance. Of course, we can start from the Ohm's law as a V by I, and that I can write in terms of the number of electrons divided by the time. And if I put this n equal to 1 and the V is the bias that, or the voltage bias that you use. This is basically the energy of the electrons divided by the charge. This should be nu, it's not small v, somehow it comes. So basically h nu is the energy of the electron divided by the charge. So I can write the V as by h nu by E, and we can write, in fact we can define the quantum resistance something like this, and as you know that this is so-called the quantum of resistance, or which is known as the so-called it was first observed by von Klitzing in his experiment. This is called the von Klitzing constant. So the quantum resistance has a value of about 25.812807 kilo ohm, and this can be easily achieved in a experiment, which is not very difficult to do. In fact, this is some kind of a structures called a MOSFET structures. So we put two gates, one gate is wired and other is, this is the second gate, and below this actually you have got a so-called some kind of quantum well, or which we call a two-dimensional electron gas system. So when you start actually biasing this gate, as you know that as you biasing the gate in semiconductor, there is a depletion takes place just below the gate. So as you see that when the gate voltage is very, very low, the depletion width is very small. But as we increase the gate voltage, as you see the depletion extends in the so-called the region where there is no gate, and ultimately at some range actually they are just before the overlapping, they give a very narrow region which behaves like a so-called the quantum wire. So this is called a quantum point contact devices. In fact, people have already demonstrated by electron beam lithography that if you make a MOSFET with a two-dimensional electron gas, put two gates very close to each other with a difference about in this case about 250 nanometer, which could be achieved easily by electron beam lithography. And if you take the conductance versus the voltage characteristics, you get so-called, you should get some kind of staircase characteristics, and which defines so-called the von Klitzing resistance about h by e square. So I think there are other possibilities. As I said, that one of the major candidates for making this solid state quantum computer is of course in addition to the spin-based materials, or in addition to spintronic materials, is this some kind of diodes called the resonant tunneling diodes. This is basically you can make either transistors with a very, very small barrier between the two n-type region, and as you see that if we put this is basically a double barrier structure. One barrier is here, one barrier is here, and this is the quantum well. So if you want to inject one electron from this side to that side, initially as you see there is no energy states here, so obviously the current as you apply the bias, the current will be very, very low. This is the point A in the IV characteristics. When you apply more and more negative bias, this electronically energy will go up. When exactly aligns with the so-called the quantized energy states in the quantum well, then there is suddenly actually a huge change of the tunneling current, just like we get normally in the optical interferometer. Exactly the same thing happens, and the current increases very sharply. But when you increase the voltage again, actually this energy level goes up. So this quantum energy states is now much lower. So obviously there is no energy states available this side in the quantum well. So obviously current actually goes down. So this is a phenomenon we call the negative differential resistance, in which we get in a typical tunnel diodes or resonant tunneling diodes. In fact, that's why it's called resonant tunneling. But ideally, if you can really confine many states within this quantum well, that's what I said, there's a real challenge to get number of states quantized in a quantum well. If you can, instead of one, if you have got 3-4 quantum states, ideally you should get a current voltage characteristics like this. Okay, this will be when it's resonant to the first ground state, when it's resonant to the second quantized state, third quantized state, fourth quantized states. So in fact, people are very excited that at least if you don't make quantum computer, at least you can make a multi-state logic. Normally, as you know, all digital circuits we do with a digital logic is 0 and 1, but this kind of resonant tunneling diodes could be implemented at room temperature. In fact, you can get a multi-state logic where I can define this is 0, this is 1 state, 2 state, 3rd state, 4th state. So obviously the computing size will go as a 4 to the power n. So that is basically the fundamental things that we want to discuss in the first part of my talk, generic. And the second part of my talk will be a little bit more about the research that we are doing using some kind of quantum dots. One of our motivation, as I said, that still we don't have the silicon lasers. At least if you have the silicon lasers, if you cannot make the quantum computer, you can make the optical computer. So one thing that whether this can be done by making quantum dots or nanostructures, because whether these, as you know that silicon is an indirect bandgap semiconductor, if you make a strong quantum confinement, is it possible to basically break the so-called the selection rule of transitions, and whether we can get some kind of emissions from the silicon or germanium. So if you want to really make a optical integrated circuit or photonic integrated circuits, you need, just like electronic circuits, you need a source. Yeah, you need a detector. You need to, transport the light or guide the light. You need the modulation. In fact, everything is possible except the light source, as I said, because this was indirect bandgap semiconductor of silicon and germanium. So now many efforts are actually going on. This is one of the efforts actually which has been reported by an MIT group in 2010. They said they can modify the band structure not by quantum confinement, but producing a lot of strain in the so-called semiconductor. In this case, they have taken a germanium semiconductor, and as you know, this is the typical band structure of indirect bandgap semiconductor. So this is actually the direct bandgap of germanium, and this is the indirect bandgap of germanium. Since this is in the lower in energy, you always have to get some kind of phonon collision, so the electron comes here and then gives rise to transition. But what they have done, they could modify by putting a lot of strain and injecting a lot of electrons in the L valleys. They could actually populate a lot of electrons in the gamma valleys, and which ultimately gives rise to radiative transition and gives rise to so-called the band gap emission in case of indirect bandgap semiconductor. So they claim it's possible to make the laser from this kind of structures, but of course not yet possible. So the next step is that whether you can make a quantum dots which can be strained and which can be with a modified selection rules, so that we can get the emissions from those things. In fact, that is possible. Now, I don't want to go to any kind of fabrication actually here, but I just wanted to mention one thing, that these quantum dots can be fabricated by so-called, as I mentioned, by electron beam lithography. You can cut the thin film layer like a quantum wire, or if you can cut this as a quantum dot, but these are actually very, very expensive process. So the people nowadays actually are thinking that it is possible to grow these quantum dots by a method called self-assembly. In fact, there are a lot of success in that. In fact, if you grow a thin film on a substrate with a different lattice, there is something called heterogeneous nucleation. So actually depends upon how much is the surface energy of the substrate and the surface tension of the material. Just like as you know that if you put a drop of water in a glass plate, it spreads very nicely. Okay, this is because the surface tension property of the water and the glass and the interface. But as soon as you put a drop of mercury, it just makes a bubble. So exactly the same thing you can do when you grow thin film on a substrate, depending on the surface energy. In some cases, they will make the bubble or the globule or make some kind of islands from the very beginning. So which is not useful for making electronic devices. In some cases, it goes a layer by layer assembly, just like a water on a glass plate. So it's a perfectly two-dimensional growth. This is typically used for so-called electronic devices or making the epitaxial layer. But there is something in between. If you make a lattice mismatch semiconductor on a thin film layer on a substrate, initially they actually spread. But since there is lattice mismatch, there is strain build up, and this strain changes the growth mode from a 2-dimensional to 3 dimensions. So they make so-called quantum dots actually by what is called, in fact I have shown almost the same thing here actually. That in this case we have taken a system of germanium on silicon. There are many other systems like indium arsenide and gallium arsenide. If you put germanium on silicon, initially they will be spread into 2 dimensions. But as you grow the lattice mismatch material, there a lot of strain energy builds up. There is a competition between the elastic energy and the surface energy. And finally this gives free energy, gives the thermodynamically they will be stable if they make this kind of so-called kind of pyramids or dot kind of structures. Those are more stable. In fact, the things that we grow in our Kharagpur is something called a molecular beam epitaxy. This is on a very old system we have about 20 years back. This is where actually you put the semiconductors for the growth, the materials like silicon, germanium in different sources, and all this takes at a very high vacuum, as a 5 into 10 to the minus 10 torr or millibird is the typical pressure. And here actually you put our sample and then load the sample from here to here in without breaking the vacuum, and then we grow the materials. So how do we actually feel that while doing the self-assembly, a transition has taken place from 2 dimensions to 3 dimensions by taking in situ electron diffraction pattern of the growth material. So when actually these materials are grown, we have got actually electron source, which is called the reflected high energy electron gun, that actually glances on the substrate and gives the electron diffraction pattern on the in a phosphor screen. So when it is a 2-dimensional growth, actually you get a crystalline, purely crystalline pattern actually of a streaky diffraction pattern. This is actually 2-dimensional representation. And when they actually, after few monolayers of these growths, maybe 4 to 5 monolayers depending on the temperature of the growth, actually there is a transformation from the streaks to actually so-called spots. So you know that now there is a formation of the 3-dimensional quantum dots or the islands, which now can be actually, the growth should be stopped and they can be used for making some kind of devices. Not necessarily they are spherical in nature, their shape actually is decided by whole thermodynamics and this total, you have to see the Gibbs free energy calculations for different kind of shapes. Typically they show different kind of shapes, they show pyramids, they show hearts, they show domes. In fact, we have got some kind of shapes, this is called, we call it this is like a half sphere, we call it a little bit of lens shaped islands, and typical density is about, depends upon which kind of growth, is about 2 into 10 to 8 centimeter square, and the height is about 4 to 8 nanometers. So as you see, this height is really much below the so-called the Bohr radius or de Broglie wavelength, but in these directions it is comparable to those wavelengths about 30 to 50 nanometer, and on a large scale sometimes actually they show different kind of distributions of the different kind of domes of large size and small size. That's why I said it's very difficult to get in self-assembly one monodispersed arrays of quantum dots. Actually, they will be of different size. But if you can be choosy, you can choose some of them and try to make some. If you have a very good lithography system, you can make a single quantum dot devices or single. Okay, if you image a single quantum dots, actually germanium quantum dot, it looks like this. This is silicon substrate, and there is a very thin layer of so-called, we call actually the weighting layer, where the growth is in 2 dimensions, and they suddenly actually transfers to so-called 3 dimensions of the, and as you see that very nice interference fringes, I don't know if it is visible from here, this basically shows that this material is crystalline. And this is as you shows the large number of quantum dots are actually aligned on a silicon substrates. So now if you want to make a devices, either you can make a single dot device or you can make a multiple dot devices. Okay, so the first observation that whether they are really the quantum dot or is that, as you know that, as I said that we don't get any light emission from silicon or germanium because of the indirect band gap semiconductor. But there is a possibility of formation of excitons. So this is a heterostructure, so there is always a band alignment in the conduction band, there is a band offset in the conduction band and the valence band offset. So holes are typically confined in the valence band, and the electrons are actually localized in the conduction band offset. So there is a strong overlap of the wave function between the electrons and hole in this kind of quantum dots, and they can form these excitons. And because of the formation of excitons, ultimately the excitons decay and they recombine and give this kind of actually called a photoluminescence. In fact, what we do, we excite these quantum dots with a lasers, and ultimately they are excited, and finally you see their recombination mechanism by experiment called photoluminescence. So this photoluminescence experiment is done for this germanium quantum dots. Normally they only show actually this photoluminescence has been taken at a low temperature like a 10 Kelvin, and we can get a very good emissions. And what you want to show this emission energy, as you see, shifts as a function of the growth or shifts as a function of the size of the material, what is called the quantum size effect. So that is actually one direct proof that if you get a size dependent shift of the luminescence or the optical absorption of the emission peak, you know that this material has actually entered in the so-called the quantum region. We get that. Only thing, as you see again, this is very, very broad because of the size distribution of those quantum dots. In fact, this luminescence is only typically exists up to about 40 Kelvin or maximum at 50 Kelvin, because this exciton binding energy is actually very, very low. If you take this system to higher temperature, the excitons actually break, and ultimately you get the quenching of the luminescence. That shows this is only good at low temperature. But the question comes, can we really achieve this emission at room temperature or near room temperature? Then definitely they will be very useful. Here we have just put some of the mechanism that we have seen. I think I will skip that. In this case, what you try to do, just like you make a crystals in 2 dimensions or 3 dimensions, what you try to do, normally you have seen this quantum dot alignment is very, very random. So our aim was to, can we make it little bit more in periodically or more in periodic order. So that's what we did some, this is called FIB lithography. In fact, this is silicon substrate and we etch different kind of holes in a periodic manner. And our aim was to put one quantum dot inside the hole, actually, in this case. But to our surprise, we see something different, because this depends upon basically the aspect ratio of the hole to the so-called the period. In fact, what we see that instead of nucleating in the island, these holes are actually, these quantum dots are nucleating along the periphery of these holes. And as you see, there is a kind of a circular periodicity. Of course, there is some randomness between the 2 holes or 2 dots. But along, I mean, if you just consider one of the dots, there is a very good circular periodicity. As soon as this periodicity is there, now there is a strong actually overlap of these wave function between these, or these quantum dots, you can say these are actually now coupled quantum dots. So in this, as soon as these quantum dots are coupled, either this one or this one, actually this one is better than the other one. And you see that we don't get any particular pattern, it depends upon the aspect ratio of this. As soon as you do this, if I try to, from the same substrate, if I take a luminescence in an unpatterned substrate, as I said that it coincidents at 50K. So after 50K there is no emission. But as soon as you get a periodically ordered quantum dots, if you take this luminescence exists well up to 200K. It only coincidents around 250K. So that is a very nice experiment. Now the people are trying to do this, doing this periodicity not only in the 2 dimensions, they are trying to put a quantum dots in 3 dimensions so that you can call say quantum dot crystals. And of course, these are very costly process, these are very time consuming process, but if you can make one quantum dot crystals, definitely, I mean, some people have shown that it's possible to get the emission even at room temperature. Okay, so the other nice application of this quantum dots can be in the case of that is for the emitter, this can be photo detectors. You can make some, as I said that if you can make a detector which can detect the black body radiation, you can basically image in the night. Not only you can image in the night, if you can really absorb the long wavelength radiations, you can do a lot of biomedical imaging. In fact, a lot of these or biomolecules like protein, DNA, they have got the vibrational frequency or the stretching frequency which comes at a very long wavelength. That's why normally people do in the FTIR. In a chemist always do infrared spectroscopy. So if you can go to such a wavelength, then definitely you can image these biomolecules and those things by using these arrays of these quantum dots, using this quantum dot as a photo detector. Now unfortunately it's very difficult to, if you want to go long wavelength or low energy, you don't have not many naturally occurring low band gap semiconductors. Only semiconductors are available is basically mercury cadmium telluride. It's very difficult to grow. These are usually used by the defense people to make some infrared camera or for night vision imaging. So the 2 other possibilities that you can get a basically transition from impurity level, either a phosphorus doped or boron doped impurity in a silicon, and get a transition of the electrons from this impurity level to the conduction band on excitation of a photon, or if you can have a number of bands or sub-bands in a particular quantum well, either in the conduction or in the valence band, then actually you can excite one of the electrons from here to here, and this actually can be actually collected as a on exposure of the photons. This is the principle of the so-called the quantum photo detectors. And as I showed, this is just I have taken some images which has been done by one of the company called, they make terahertz detectors and the scanners. And they have shown that if you can really go to the frequency range of the terahertz, you can do the detection of the cancers, because the composition of a cancerous cell is different from the non-cancerous cell. So different kind of skin cancer, liver cancer, etc. They could be done by medical imaging. In fact, many people are doing that. This gives rise to very good, nice spectroscopic information. So I know that people try to image that whether I can image anthrax, whether it is different from normal white powders. So this kind of images has got a lot of applications for the security applications, particularly security as a biomedical imaging. So I'll skip that. we did some work actually with one of the group in University of Delaware to make this photo detectors in the terahertz range, but I will not present that result. I just present one result from our group which we have done. In fact, this transition selection rules actually depends upon whether we make a quantum well or quantum dot. In fact, in quantum well, this transition selection rule is not very favorable to make a normal incidence photodetector. So that's why most of the people actually put a grating. But if you make a quantum dot, it is confined in 3 dimensions, it's easily possible to have a normal incidence detector. So that's why the quantum dot is very favorable than the quantum well. So what about the quantum dot that we grow in our MB? Actually, it's a very large area quantum dots. Actually, put in a structure, we put a silicon substrate, and then we put some kind of a dopants into it. And finally, we made there actually the response in the so-called the mid-infrared range. In fact, we are trying to make some mid-infrared range detector in the range of about, typical good wavelength is between 8 to 12. But our quantum dot, we got the response, good photo response only at about 6 to 7 micron wavelength. And as you see that this again, this works at room temperature because these quantum dots and actually the leakage current is very, very low. Of course, the noise is very high, but as you cool them, actually their photo response is very, very high, and this gives rise to detection. And this works at a very low voltage. Normally, a photodetector, you have to always bias it, but in this case, even if it is a bias as low as 0.1 volt, it gets a very good so-called photo response. In fact, this is the band energy diagram. In fact, when I was talking about the photoluminescence, I was talking about that one hole is confined here and electron is localized here. So there is a strong wave function of the overlap of the wave function that gives rise to emission. In case of the photodetector, actually the hole is localized in the valence band of the germanium. So basically they first are excited to, there's one more layer actually in this case. I will not go to the details, this is a little bit of the growth actually. So there's one energy quantized in the quantum dot and one energy in the so-called waiting layer. So there is always, there is a 2 wavelength. In fact, you could model this 2 wavelength by using this energy band diagram. So in the summary, what I want to report is possible to make this quantum dot not only as a emitter, it's possible to make them as a detector, and which works at a, so-called long wavelength. Now the question is that can you charge these quantum dots? If you can charge these quantum dots, and if this charge does not decay, you can ideally use as a quantum dot memory. So that is some of the experiment that you have done. Actually, this is again the room temperature experiment. If you do this experiment low temperature, you are supposed to get much more better result. This is done by an instrument we call conductive atomic force microscopy. I know the atomic force microscopy is used to do the topographic image of a quantum dots. So this is the sample that we have taken, the topographic image of the quantum dots. Now if you use a conducting tip, actually it's a conducting tip, and we come very near to these quantum dots, and if you take a current contrast imaging, we exactly get this kind of structure which replicates that topographical image. So this is the current contrast imaging that shows that charges are actually transferred to the quantum dots when you apply bias. In this case, these images are taken at this V equal to 300 millivolt, 500 millivolt. So in fact, our substrate was p-type, and typically this germanium quantum dot, as I said, that there is a quantization energy level for the holes. So if you have the positive bias on the substrate, these holes are injected into these quantum dots and they charge themselves. And if you keep it, normally it is not removed. It can be only removed even if you take out the bias and you do a 0 volt imaging. Of course, there is some charge leakage, but still shows that. But when you apply a negative bias, then only you can remove some of these electrons from these quantum dots. That shows that these quantum dots can be used for a single electron memory or single dot memory devices very nicely. In fact, if you do a calculation, take each size of each quantum dot, and in fact, ideally, if you try to find out what is the charging energy of these quantum dots, typically charging energy for a 1 nanometer quantum dots actually is about, if you take a gallium arsenide of about 10 nanometer size, actually the charging energy is about 11 millielectron volt. That means, and this 11 millielectron volt is very easily measured. That means we can get after each 11 millielectron volt, millivolt actually, that one of these electrons will be added to this so-called this quantum dots. So this is actually, it's called the Coulomb blockade phenomena. In fact, we also got this kind of, as I was telling you that we got some staircase characteristics when you could take some of these conducting AFM tips on one of the single quantum dots. But as you see that there are a lot of noisy things also, because these are taken at room temperature, again I am saying. So normally people have demonstrated by the STM that if you can do this low temperature STM experiments, you get a very nice IV characteristics with a lot of staircase. But our things was mixed with a lot of other noise also. And we have found this charging energy is about 0.053 electron volt, which is much more than actually that room temperature energy. That's why it could be achievable at room temperature. That depends on the size of these quantum dots. Okay, so these quantum dots actually, not only that this can be actually embedded in a high band gap matrix also, or like an oxide matrix. In fact, these quantum dots can be used for making a solar cell applications, making many other photonic devices. But one of the main problems is that how to embed in a defined kind of material. In this case, actually, you could show that there are many other groups. These quantum dots can be actually embedded in a high band gas silicon dioxide matrix. And when you put in the high band gas silicon dioxide matrix, this photoluminescence intensity is very, very strong. And that can be achievable at room temperature. In a MBE ground quantum dots, we could see only up to 50K or 40K, or after making a periodic array, it was up to 200K. But since the confinement potential is very strong, because silicon dioxide has the band gap about 9 electron volt, and germanium has the band gap about 0.7 electron volt, they have a very strong confining potential. That gives rise to actually give a luminescence at room temperature. When you get a, this is basically different samples name. The sample was prepared at 1000 degrees centigrade. If you sample a prepared lower temperature, they typically gives actually some kind of a defects of the amorphous peaks. So, and basically we see if you again the same thing as you see the quantum size effect. If you vary the quantum dot from 2.4 nanometer to 10 nanometer, actually the size of the photoluminescence. Of course, for the device people, or if you go to the electronic engineer, you will not believe this photoluminescence. They said, can you give me some device, I will put a battery and the light will come on. So that means this phenomenon is called the electroluminescence. You apply the electric field, and if you get the electron hole decombination, then the light comes on. So in fact, we have made some kind of structure with these quantum dots in a different oxide matrix, like a aluminum oxide matrix in this case. And this silicon dioxide is a very thin silicon dioxide which acts as a very thin tunneling thickness, so that the holes can be injected from this side and the electrons can be injected in the quantum dots from this sides. And then basically we try to detect this emission by a fiber optic coupled system. And of course we get a very nice emission, as you see that up to, in this case, these two different samples I am showing. I mean, this is a better sample. So typically you start getting the emissions up to 6 volt, and as you start increasing the voltage of the bias, actually that emission intensity or electroluminescence intensity goes up. So here you don't have to excite quantum dot by the laser. So this is electrically operable so-called devices. And yeah, forget about this. This is a different sample with a little bit more defect. So this works better. And this electroluminescence peaks actually is almost in agreement with the photoluminescence peaks that you see over here. And probably the last 2 slides or so, that as I said that these quantum dots actually, if they are embedded and they are isolated, in fact, this is one of the first demonstrated in the IBM first by 1996 by Sandeep theory, that these quantum dots can be used as can be charge trapping nodes, and if they can be used as charge trapping nodes, they can be used as a memory. So it is something like this. If you take a IV characteristic of a normal MOSFETs, the typical IV characteristic is like this. You apply a voltage. After a threshold voltage of V, there will be a lot of current flow. Now, if you put these quantum dots or nanocrystals inside these MOS gate oxides, they can trap the charges. So if they trap the electrons, so next time actually you have to apply much larger voltage, because since these electrons are, these dots are charged, so they will basically screen the potential that you are applying to the gate. So you have to apply more potential to switch on the devices. So this can actually use as either one of them can be 0. So that means you want a high threshold voltage and a low threshold voltage. And in fact, this can be easily actually can be seen by taking either a current voltage characteristics or the hysteresis in the capacitance voltage characteristics. So in the that we have seen actually that hysteresis varies as a function of actually what is the sizes you are doing. If the density is more, the hysteresis is more. So ideally, this can work, and we have seen the hysteresis in not only the capacitance voltage, it shows the hysteresis in the conduction voltage. And if you see this, ultimately for the device people, you have to show that ideally this charge should not leak, because since this quantum dot is embedded in a very good insulator, this charge should never leak. But as you know, there is always some defects in the insulators. So since there is a lot of little bit of defect in the insulators, so this threshold voltage actually comes down as a function of time. And in fact, we do the measurements up to 10 to the 4th cycle and extrapolate up to about 10 to the 8 cycles, and we still see a good hysteresis width, so that it shows that this can be usable in fact, a lot of companies are making now silicon-based nanocrystal memory. So I'll stop here, and to conclude, actually, probably these are some of the conclusions, some of the trends where the nanoelectronics or nano devices may go in future. So we are still working, people are still in the electronics, people are working on silicon insulator, vertical small structures. But definitely if you can get this resonant turning diode single electron structures which have been demonstrated actually in the R&D, if you can really make them as a commercially possible devices working at the room temperature, they can be used as the building blocks of the quantum computers in the future. So I don't want to predict anything, but most of the predictions about the computers have been grossly wrong. As you see, 3-4 quotes I want to put. These are the famous quotes by that IBM chairman Watson, that there can be maximum 5 computers. Of course, in 1943, 1949, there's one more prediction in one of this thing that about the weight of the computer. Okay, this is the president of the DEC Corporation. These are all big shot people. So they made all the predictions which are totally wrong today. And finally, by the Bill Gates in 81, he said probably 64 kilobyte of memory should be enough for anybody. You don't need anything more than that. So that means all these predictions are wrong. And if you want to predict about the nanotechnology or some nano devices, lots of hypes. In fact, we can see and go to many schools of engineering colleges have started doing MSc nanotechnology, MTech nanotechnology. You have to be very, very careful before giving them the degree, because the future is not always great. This is Eric Drexler, actually he wrote a kind of a very popular textbook that you can make robots out of molecules, and the robots will do all kind of a computation architecture like this. And Nobel laureate Richard Smalley says that it will be never achievable. So that's why you should be very careful for making this thing, any predictions. And so of course it's a misguided promise that this nanotechnology can solve everything. So thank you very much.